Welcome everyone. Today, we'll explore fracture mechanics, a discipline that helps us understand how cracks initiate and propagate in materials under stress. This knowledge is crucial for predicting failures and ensuring safety in high-risk industries like oil and gas. Purpose and scope of fracture mechanics. Introduction and objectives. Fracture mechanics is a critical discipline in engineering that focuses on understanding how cracks initiate and propagate in materials under stress. Its purpose is to predict failure modes and ensure structural integrity, particularly in high-risk industries such as oil and gas refining. This field bridges materials science and applied mechanics, providing tools to assess flaws that cannot be eliminated during manufacturing or operation. The scope includes evaluating crack growth, determining safe operating limits, and guiding inspection strategies. By applying fracture mechanics principles, engineers can prevent catastrophic failures, optimize maintenance schedules, and comply with standards like API 579 Part 9 and BS 7910. These standards provide methodologies for flaw assessment and fitness for service evaluations, ensuring that components operate safely within their design life. Understanding fracture mechanics is essential for refinery inspections because equipment often operates under high pressure and temperature, making it susceptible to fatigue and stress corrosion cracking. The ultimate goal is to maintain reliability, reduce downtime, and protect personnel and the environment. Basic principles and historical context, fundamentals of fracture mechanics. Fracture mechanics emerged as a response to catastrophic failures in structures where traditional design methods based on stress analysis proved insufficient. The discipline introduces concepts such as stress intensity factor or K, fracture toughness or KIC, and energy release rate to quantify the severity of cracks. Unlike conventional strength-based design, fracture mechanics considers flaws as inherent and focuses on their growth under cyclic or static loads. The historical development began with Griffith's theory of brittle fracture, which linked crack propagation to energy balance. Later, Irwin extended these ideas to metals and introduced the stress intensity factor, enabling practical applications in engineering. Today, fracture mechanics is applied across industries to predict failure, design inspection intervals, and develop repair strategies. Its relevance in refinery operations is profound because components like pressure vessels and pipelines experience complex loading and environmental conditions. Understanding these fundamentals allows engineers to interpret inspection data accurately and make informed decisions about continued service or repair. Key concepts in fracture mechanics: flaw idealization and classification, stress intensity factor or K and fracture toughness or KIC, crack growth and fatigue behavior. Flaw idealization involves simplifying real-world defects into geometric shapes that can be analyzed mathematically. Common flaw types include surface cracks, embedded flaws, and through-thickness cracks. These are often represented as elliptical or semi-elliptical shapes to facilitate calculation of stress intensity factors. Classification is essential because the severity of a flaw depends on its size, orientation, and location relative to stress fields. Standards like API 579 Part 9 and BS 7910 provide guidance on categorizing flaws and selecting appropriate assessment methods. For example, a small surface crack in a low-stress region may be acceptable, while a similar crack in a high-stress zone could lead to rapid failure. Idealization also accounts for residual stresses and environmental factors such as corrosion, which can accelerate crack growth. By accurately modeling flaws, engineers can predict their impact on structural integrity and determine whether repair or continued operation is feasible. The stress intensity factor or K quantifies the stress state near the tip of a crack and is a function of applied load, crack size, and geometry. It is a critical parameter because it determines whether a crack will remain stable or propagate. Fracture toughness or KIC represents the material's resistance to crack growth under mode I loading, opening mode. When K exceeds KIC, unstable fracture occurs, leading to sudden failure. These concepts form the basis of flaw assessment procedures in API 579 and BS 7910. Engineers use K and KIC to establish allowable flaw sizes and safe operating conditions. For refinery components, where high pressures and temperatures prevail, accurate determination of these parameters is vital. Materials with high fracture toughness can tolerate larger flaws, while brittle materials require stringent inspection and maintenance. Understanding the interplay between K and KIC enables predictive maintenance and enhances safety. Crack growth occurs when cyclic or sustained loads cause a flaw to extend over time. Fatigue crack growth is particularly relevant in refinery equipment subjected to pressure fluctuations and thermal cycles. The rate of crack growth depends on factors such as stress range, material properties, and environmental conditions. Paris law is commonly used to model fatigue crack growth, relating the growth rate to the stress intensity factor range. Corrosive environments can accelerate crack propagation through mechanisms like stress corrosion cracking. Monitoring crack growth is essential for planning inspections and repairs. Standards like API 579 Part 9 provide guidance on predicting remaining life based on crack growth models. By understanding these principles, engineers can implement proactive maintenance strategies, reducing the risk of unexpected failures and optimizing asset performance. Application in refinery inspections, fitness for service assessment, inspection workflows and case studies. Fitness for service or FFS assessments determine whether equipment with flaws can continue operating safely. API 579 Part 9 provides detailed procedures for fracture mechanics-based FFS evaluations. These assessments involve calculating stress intensity factors, comparing them to material fracture toughness, and predicting crack growth under operating conditions. For refinery components such as pressure vessels, heat exchangers, and piping, FFS assessments are critical because shutting down operations for repairs can be costly. By applying fracture mechanics principles, engineers can justify continued service for components with acceptable flaws, schedule repairs during planned outages, and avoid catastrophic failures. This approach enhances safety, reliability, and cost-effectiveness. Refinery inspection workflows integrate fracture mechanics to prioritize inspection intervals and methods. Techniques such as ultrasonic testing, radiography, and magnetic particle inspection detect flaws that are then evaluated using fracture mechanics principles. Case studies demonstrate the effectiveness of this approach. For example, a pressure vessel with a detected surface crack was assessed using API 579 Part 9 procedures. Calculations showed that the stress intensity factor was below the material's fracture toughness, allowing continued operation until the next scheduled shutdown. Another case involved piping with multiple flaws where crack growth analysis guided the decision to implement temporary repairs. These examples highlight how fracture mechanics supports risk-based inspection strategies, optimizing resource allocation and ensuring safety. Let's summarize and see the future outlook. Fracture mechanics provides a robust framework for assessing structural integrity in refinery operations. By understanding concepts such as flaw idealization, stress intensity factor, fracture toughness, and crack growth, engineers can make informed decisions about inspection and maintenance. Standards like API 579 Part 9 and BS 7910 offer practical methodologies for applying these principles in fitness for service evaluations. The integration of fracture mechanics into inspection workflows enhances safety, reduces downtime, and optimizes costs. Future developments may include advanced modeling techniques, real-time monitoring, and predictive analytics to further improve reliability. Embracing these approaches ensures that refinery assets operate safely and efficiently throughout their lifecycle.